Students, we shall resume the study of Bohr model of atom. As told earlier, you find the nucleus contains protons and neutrons, and around the nucleus at definite distances we find the orbits. Orbits are designated the letters K, L, M, N, O, P, etc. And the filling will be in the order which follows Bohr concept, which states that the maximum capacity of each shell will be given by 2n square, where n shows the energy level which starts from 1, 2, 3, etc. up to n. So the first shell closest to the nucleus, that is the K shell, will have n value equal to 1. So on substituting it in the Bohr concept, we can get the maximum capacity of the orbital. So maximum number of electrons accommodated in K shell will be given as 2 into 1 square, which is equal to 2. The next orbit L shell can have n value 2, and so its maximum capacity will be 8. Likewise, if you just substitute the values for the energy levels, we can get the maximum electrons that can be accommodated in each and every orbital, and it follows the pattern 2, 8, 18, 32, etc. Associated with each orbit, we have the energy levels, and here you find that the K shell, suppose it is having the energy level of E1. L shell will have E2. Evidently, the energy of E2 will be more than that of E1. So, what is the difference in energy? Difference in energy is given by delta E, which is equal to E2 minus E1, and that is found to be a packet of energy which is known as a quanta, which is h nu, where h stands for the Planck's constant, which amounts to 6.626 into 10 power minus 34 joules seconds, and nu stands for frequency, which is related to wavelength by the equation nu is equal to c by lambda, where c stands for the speed of light in vacuum, that is 3 into 10 raised to 8 meter per second. Now that you have understood the Bohr model of atom, now we will see what happens to an electron when it absorbs some amount of energy. Suppose an electron is present in the K shell. As long as it moves in the K shell, there is no energy change for the electron. But as soon as it absorbs some energy, it jumps to the higher levels. Then we say that the electron gets excited. The most stable state of an electron, that is known as the ground state. From the ground state, on absorbing certain amount of energy, either in the form of heat or light, it will jump to the higher levels, and then we say that it is in the excited state. The excited state of electrons are highly unstable, so it tries to come back by radiating energy. In the process, we find that we get different spectrum. This was later identified as line spectrum. We are going to discuss the line spectrum of hydrogen. We know hydrogen has the atomic number 1 and mass number is 1. So you find that there will be 1 proton, 0 neutron and 1 electron. The first electron, the only electron that is present in hydrogen, will be placed in the K shell. So this represents the ground state of hydrogen. But when it is irradiated with light or heat, you find the electrons are just jumping to the higher levels, then it is said to be excited. When it is in the excited state, it tries to come back by releasing energy. Hydrogen atom, after absorbing energy, reaches the higher level, and when it tries to come back to its original state, it releases lot of energy, and these radiations were recorded, and we get what is called the line spectrum. We have a series of line spectrum obtained for hydrogen. For example, the first series that was discovered was by Balmer, and that falls in the visible region of light, and that is known as Balmer series. Later, many scientists did experiments with hydrogen and they were able to reveal the actual line spectrum of hydrogen, which consists of about 5 different sets of radiations, 5 different series of radiation. Once the electron has reached the higher levels, when they come back to its original state, if it is coming back to n is equal to 1, we get what is called the Lyman series. Instead, if the electrons settle down at n is equal to 2, we get the Balmer series. Similarly, if the excited electrons come back to n is equal to 3, we get Paschen series. Then, if it is resting at n is equal to 4, we get bracket series and so on. So, we can just identify the line series as follows. The illustration seen here explains the line spectrum of hydrogen. The first level we have here is n is equal to 1. Second energy level is n is equal to 2. N is equal to 3. N is equal to 4. N is equal to 5. N is equal to 6. N is equal to 7. And the last one we represent it as n is equal to infinity. So this diagram represents the line spectrum of hydrogen. So when we told earlier that when the excited electrons come back to n is equal to 1, we get the series which is known as Lyman series. So this was identified by the scientist named Lyman, and it belongs to the ultraviolet region of the solar radiation, so that cannot be seen. Then comes the Balmer series. In which the excited electrons come back to n is equal to 2. This is belonging to the visible region of light, and this was the first series that was identified for hydrogen. Coming to the next series where the excited electrons come back and settle down at n is equal to 3 is known as Paschen series. This also cannot be visible to us because it belongs to the infrared radiations. And the next series is known as bracket series, where the excited electrons come back and settle down at n is equal to 4. This also belongs to infrared region. And then we have the Pfund series, which belongs to the far IR region. So that is also not visible to human eye. And the last series is known as Humphrey series. Humphrey series, which belongs to the IR. So the line spectrum can be summarized to be made up of 6 different series starting from Lyman, Balmer, Paschen, bracket, Pfund and Humphrey series. Lyman series, you find that the electrons settle down at n is equal to 1, whereas in Balmer it settles down at n is equal to 2. Passion, bracket, Fund, and Humphrey, it follows the next higher levels respectively. And you find that the spectral regions in which each of them are present will be as follows. Lyman, it belongs to ultraviolet region of the solar radiations. Balmer, it comes in the visible range. Passion, you find it will be the near IR region. Bracket, Fund, all comes under IR region, and Humphrey comes to the far IR region. So here you find that this is the near IR region for passion. Bracket, Fund, you find it will be followed by the IR regions. Fund, it is actually far IR, and Humphrey also belongs to far IR. Bohr model of atom was able to explain successfully the line spectrum of hydrogen. It also points out the fact that the energy levels are discrete or fixed. So you find that quantization of energy is true in the case of Bohr model of atom. He was also able to explain the energy change happening during a transition. He gave the expression delta E is equal to En minus Ei, that is E final minus E initial, which is equal to 2.18 into 10 power minus 18 into 1 by n I square minus 1 by n f square. This much joules. We also know the fact that E is equal to h nu. So, delta E is equal to E2 minus E1, which is equal to h nu, from which we can calculate the value for frequency. Nu is equal to delta E divided by h, where h stands for the Planck's constant. Once we have calculated the frequency, we can also calculate the wave number nu bar, which is related to frequency by the relation nu is by C is equal to nu bar, which is equal to C by lambda into C, which gives 1 by lambda. So, you find that wave number is nothing but number of wavelengths per unit length, and it is known as nu bar, and its unit is meter raised to minus 1. In short, Bohr model could explain the line spectrum of hydrogen effectively. It also can explain the quantization of energy, that is, energy levels are having fixed values, and it also explains the stability of atoms. But the limitations are in plenty for Bohr model. It is applicable to only one electron systems, that is, it can be explained only for hydrogen or hydrogen-like species like helium plus, lithium 2 plus, etc. It also could not explain the splitting of spectral lines in the presence of electric field and magnetic field, that is, Zeeman effect could not be explained effectively by Bohr model of atom. What do you understand by Zeeman effect? It is splitting of the spectral lines in the presence of an applied magnetic field. Why splitting occurs cannot be explained by Bohr model. Same is the case with Stark effect. What is Stark effect? Stark effect is splitting of spectral lines in the presence of an applied electric field. Here too, Bohr was not able to explain it successfully. Another point is that Bohr could not explain why atoms combine to form molecules. He explained that atoms as such are stable. It is neutral in nature. Then why do the atoms combine? Question remains. Since demerits are in plenty, a better model was suggested which is followed even now, and that is known as quantum mechanical model of atom. That we will be learning in the next video. Thank you.